The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. We will be starting the webinar in a few minutes from now. Hello, everyone, and welcome to today's webinar. Today's webinar will be given by Amod Onkar, our expert for 5-axis and HSM, and it will be about the new functions in 5-axis and HSM. Notice that this webinar will be also recorded and available after in our reseller area. During the webinar, if you have any questions, you can write them down in the question bar and Amod will attend them after the webinar itself. Also, one important thing that I want to remind all of you is that we have a very important post-processor training coming up in Germany on the 4th and 5th of September. As you can see on my screen, we've sent an invitation by email. When you can register, you have a link to register. Then you have also a link to see the agenda and the hotel information for your convenience. So, Amod, you can start. Everyone, enjoy.
Thank you very much, Natalie. Hello, everyone, and welcome to this webinar. Today, we're going to see the new features of 2018, and I'm going to show you some features that probably will be seen in the next SP release also. Very important features. I believe that you should know them. So let me start with the first new feature that we introduced in 2018, and that was a completely new module for machining screw type parts, and we call that module screw machining. Now, typically, parts like what you see on your screen on the screen right now are the applications that can be handled by this particular module. But what I've also seen with a few of my requests and applications that came in, any component that is round and it's being done on a 4-axis machine can become a potential application for screw machining, especially if there are fins on the part. It's a round part and there are fins placed at irregular intervals and they are not symmetrical. So such components can become a potential application for screw machining. Whether you would like to do roughing or you'd like to do finishing, they are very typical applications for screw type parts. Now, the difference between let's say an impeller or a port and a screw is simply the way the slicing happens. So if I go to my front view here, okay, if I go to this view, what the software simply does is it understands what is a stock that's been defined by the user, and it knows the lowest point or the lowest point on the part, and it knows the highest point on the part. Remember that this is a 4-axis application and it'll always consider things to be cylindrical. So what it simply does is it simply keeps offsetting the inside or the outside cylinder till it meets the inside cylinder, and at each offset, which is defined as a depth of cut by the user, it will create a slice, and this slice will be cylindrical slices. And in the end, it will just create a morphing kind of a toolpath between those slices that it has generated to create a roughing toolpath. Now, the creation is as simple as doing any 3-axis part. What you really need to define in screw machining, you really don't need to break your head on the definitions, but what you can simply see here is in the geometry, I can select the strategy for machining. You can either do a roughing or you could directly do a finishing operation. In the pattern, you have got a couple of options, offset and spiral. In offset, it will just keep on offsetting. For example, let's look at an area here. Okay, let's look at an area here. Let me switch off this tool at the moment. Let's look at the area here. We have got quite a lot of space that's there after the fin is finished. So even in this area, if I select the offset option, it will just keep offsetting the profile that it gets. Okay. But if I use the second option, which is offset and spiral, the offset will stop exactly at this point. No more further offsets will be created. And the remaining area here will be a simple spiral toolpath, which will be wrapped around or which will have a profile similar to a circle, just an offset of circles. It's no longer going to take the shape of the blades. Okay. So these are the two strategies that have been given, the patterns that have been given. In terms of machining surfaces, you can see that we no longer select individual surface. We select the model as it is. Now, this is where the difference is between the screw machining module, the impeller module, or the multi-blade module, or the port module. In the port or even in multi-blade, we are forced to select surfaces. Although the application is completely automatic, the selection is we need to individually select surfaces to tell to the system what is a floor, what is a hub, what is the blade surface. But here, I can simply say, this is my part to be cut. I don't need to define what is my floor, what are my fins, nothing. The software is smart enough to analyze and understand what is the floor and what are my fins. So once this is defined, if I want, this is an optional thing, I can define machining area. Now, machining area can be defined in a couple of ways, because in a round part, you can have two different, or a cylinder can have two different machining areas. The first machining area will be along the length. Okay, so I can specify a point to start from and a point to end. So it will only machine the part between those 2 points. So I can be very specific. I can say start from this point and go only up to here. So it will machine only this area here. Or if I could say start from here, this point, and all the way here, it will machine the entire point. So this is one way of defining the limits of machining for cylindrical areas. The second limit is pretty interesting because we work with the different limits. We go to the front view and we'll ask the user here in the axial limits, what is, the radial limits, what is the start and what is the end, okay? So our start is 0 degrees and our end is 360 degrees. So it encompasses the entire circle. I can say machine only between 0 and 90. So it will only machine this quadrant here. Or if I say machine 0 to 180, it will machine half of this screw. 0 to 270, it will machine 3/4. And 0 to 360, if I don't give any limits, it's assuming that I want to machine the entire part. So here the limits can be defined both in the length as well as the radial angles. If I have not defined any of these, that means I would like it to machine everything. And the offset, basically just what is the stock you would like to keep for the next operation. The tool definition, we support ball nose, bull nose, and flattened mill for roughing and finishing. The three standard tools are supported by screw machining. In the levels, you can see that most of the things are automatic. The only thing that has been left to the user are the retract distances, entry and exit distances. So we have tried to make it more automated. The toolpath parameters, tolerance, and you have the step down where you can specify a constant step down or you could specify a maximum step down, both in terms of percentage and the distance. And then you have the step over, which is basically our distance between two passes on the same layer. In the sorting, you could have zigzag, and the direction is 1 or direction 2, depending on which side it is cutting. Definition of stock, you could have or you could define stock based on auto-updated stock. That means whatever stock you've defined as a start in SolidCAM could be used directly inside screw machining, or for some reason your customer has said, I am actually not going to machine this area here. This is a waste of time for machining with milling. This side also is waste of time for machining with milling. So I'm going to give you a pre-turned block. You use the pre-turned block as your stock. In that case, you could also pick that pre-turned block based on the surfaces, the external surfaces of the pre-turned block. Or if you don't know what is going to be the stock, you could ask for a bounding cylinder, and that cylinder will be created by SolidCAM automatically. You can see that in tool axis control, it's just 4 axis, and it'll only ask me what is the 4th axis rotating around. So in our case, it is around X, and the base point, the point from which at the 4 axis is rotating, is the 0, basically our origin. Well, this is all that is needed for defining our roughing, and what we get here is a simple, nice toolpath. Okay, I have already calculated this operation. Why? Because I don't want you to wait 3 to 4 minutes in front of the system just looking at the calculation. So I've already calculated it, and this has taken me about 3 minutes to calculate. And the size of this part basically is, if I check the length, this is about 400 millimeters. So it's a pretty, it's not a small part, but neither it's a pretty large part, but it's somewhere a medium sized part, a 400 millimeter. And let's look at what diameter it is. So let's make a simple sketch because I don't know what diameter it could probably be. Let's go to the front view. Okay, and I'll just pull this up. roughly. So this is the diameter. It's about 120. Okay, so we have a part that is 120 millimeter diameter and 400 millimeter in length, which I would generally call a medium-sized part. And this part, the calculation time is about 3 minutes. Now, imagine the same part given to you, and you're going to work on using our generic 4 and 5 axis engine. This part could take anywhere between, the calculation would be pretty quick. It would probably take a minute. But to get to that minute, the amount of work that you need to do to get to that minute would probably be an hour or two before you get the right result. But here it's simply like doing a 3-axis machining. Select a part and hit the calculate button, and it will do the calculation for you. The same technique then is carried over, and instead of doing roughing, we basically will do the finishing operation. And you can see that I've now given the actual limits out here. I don't want it to go anywhere else within a specified distance. I would like it to machine. And it simply will ask, what is the depth of cut? 1 millimeter in this case. Okay. And what do I get here? Everything else remains the same. What do I get here? I get a pretty nice toolpath here, which runs all around the part. Okay. Again, here, a generic engine would probably do this in about a minute or two, including the gouge checks. But then you're not sure of the result. You'll have to run several checks before you come at the final result. So again, it could take anywhere between 30 minutes upwards to an hour. Whereas here, the calculation was done in like 3.5 minutes. So the calculation time, when you compare it to our generic time, just the plain calculation, like the number crunching, this could sound slow. But to get to the result, this is dramatically faster when you compare it with a generic 4-axis engine that we have. So this is a very dedicated module that we have introduced in 2018 for such parts, including parts that are cylindrical. Like I said, you have a cylindrical part with a lot of fins on it, placed at different intervals at different angles. You could just rough it out using the screw machining module. We have named it screw, but it doesn't mean that it will be used for machining only screws. It can be used for machining any part that's cylindrical and that's going to be machined on a 4-axis machine. It's along X or along Y. Okay, so you could use this module for different purposes apart from just doing generic screw machining. Okay, let's move on to our next subject, the next things that we introduced in 2018. So let me open a file. What we introduced in 2018 was an addition to our swarfing engine. What we have inside swarf is in tool-axis control, you have now a new output format for 4-axis. So you could use a swarfing engine to machine 4-axis parts like this. For example, I know that you could say that, hey, I could use my wrapping function to machine. Now I have just created a simple geometry. You could create a complex geometry on a 4-axis machine, and that could be used for machining with swarf. So you have got an option of using 5-axis. You also have an option now introduced for 4-axis, and we also have an option for 3-axis swarfing. So if you have simple prismatic parts with some complex geometries on it, you could use that to do swarfing for 3-axis, single pass or multiple passes. Okay, let me just disable this. Okay, it's already disabled. Right, so you have got an option now for creating swarfing toolpaths for 4-axis, and this is how it would look like. So if I run the simulation, let's reduce the cycle. Yeah, that's one. And then let's go to this portion here. Yeah, so this area is done, and they could also go to this area out here. So swarfing now allows you, other than 5, it allows you to define even 4-axis swarfing, or you can use swarfing on 4-axis machines, or you could also use swarfing for simple 3-axis geometries with complex surfaces on it, you could use swarfing. So this is another new thing that we introduced in 2018. All right. A very important thing was also introduced in 2018, and this was something that our users have been asking from a pretty long time. And this is basically support of circle end mills, okay, which is basically barrel and oval form tools. Now, what are these tools? If I go into my tool library, you could probably look at this tool now. Let's increase our size, and let's look only at this area here. An oval form tool or a circle type end mill has got two radiuses. It has got one large radius here and one small radius at the end. So it's a dual radius that we have. Why are these tools so popular, or are getting so popular now that software will have to start supporting them? The reason being that when you're doing a scallop calculation on a part, let's assume we have got a part with a large radius and we would like to machine that. If I use a tool, let's say this tool's diameter is 16. So if I use a 16 ball nose, the front of the radius will be R8. Okay, it will be a small radius. Now, if I want to use the R8 radius and generate a scallop of, let's say, 5 microns, I would probably need a step over of about 0.3 or 0.5. Between that, I will need a step over to generate a scallop of 5 microns. Now, imagine instead of R8, if I give you an option to determine a scallop on a very large radius like R90, the same step over now jumps to 1.5 millimeter to give you the same scallop of 5 microns. That means my step down instead of 0.3 is now 1.5 millimeter, which means it's like 5 times faster. The feed rates, even if I keep the feed rates the same, I'm actually completing a part 5 times faster than my conventional tools that I use like ball nose and bull nose. So that is one of the reasons why circle type end mills are becoming popular. Now, it's not that you can use circle type end mills everywhere. You cannot. But they do cover a lot of spectrum of paths where they could be applicable, like the part now that you're going to see, a simple turbine blade part. Now, if I take a 16 millimeter ball nose tool, and if you'd like to cut this entire length of the part with a particular tilt angle, and I would need to generate a scallop of 0.005, I would need a step over of 0.5. Okay, whereas the same thing with a oval form tool, I could generate the same scallop of 0.005 with a step down of 1.5 millimeters. So it's like 3 times, not 5 times, 3 times faster, which is quite a lot of savings when you compare it with conventional cutting. Now, there have been questions asked to me, okay, on what should be the tilt angle. It's obvious that if I have this tool, okay, if I have this tool here, and I would like, let's assume that I'm just cutting a straight surface. I'm cutting a straight surface. So if I keep my tilt angle 90, I will have this portion of the tool in contact, the upper portion, the place where the cutting edge ends. That's going to be in contact. I don't need that. So what should be my tilt angle? Well, it's very difficult to define a particular value as a tilt angle. But our goal should be to use about 15% below this and about 15% above this particular radius. That means this area is what we must look at to use when we cut parts. It's not a good idea to go completely down. That means to give a very large tilt angle. If you give a pretty large tilt angle, there is always a danger of this portion coming in contact with the material, and that will ruin your concept of going fast. If you give a pretty less tilt angle or no tilt angle at all, again, you're in a danger that this portion is going to be in contact with the material. If the shank is also of the same diameter, there's a possibility that the shank could start rubbing against the finished area. So it's always advisable to find, I mean, this is a simple mathematical calculation to find what would probably be the best tilt angle, let's say at a point here. It's simple for us to calculate. All I need is this geometry, a point here, and all I need to make is a tangent line, and I can make tangent of that line at this point and find what probably could be the angle of tilting that I need to generate maximum contact of the radius portion, the large radius portion, onto the geometry as far as possible. Okay. Sometimes, if the geometry is completely open on both sides, it makes sense to keep the contact point somewhere in this region here. But if you think the geometry is closed at the bottom, like in this case, I have got the geometry that's closed at the bottom. Okay, it's closed at the bottom here. It stops. We need to stop the tool. In that case, if you still insist on this point to be taken for the tilt angle, will decide the point, assuming that we have calculated a tilt angle, let's say of 20 degrees, and that 20 degrees is making this point in contact with the material, I will have uncut area remaining at the bottom, because the moment this point hits the bottom surface, the calculation ends. So if you get into this situation that you would like to use maximum amount of your tool's cutting edge, large radius, then it's always better to drop it down to somewhere to this point. You'll still have some uncut area, but that's unavoidable, that you can finish it with the further radius of this itself. You don't need to have another tool. You could provide a bigger tilt angle and use the front of the tool to finish the remaining area. So the tilt angle will depend on the geometry. If the geometry is open, I would always use somewhere at the center of this. That will be the best portion. A lot of rigidity you'll get. And if it is closed at the bottom, I would probably go somewhere in this region here to give the tilt angle slightly more than what I would have given for the center area. So the tilt angle in this case I have used is about 10 degrees. You can use 15 degrees, you'll still get a good result. So this is my tool path for machining this part. And this is 1.5 millimeter step down. And even if I keep the feed constant, I still end up cutting this part 3 times faster. Now, how do you calculate the scallop? When I send you this part, you will see that in this part there are 2 sketches. Okay, there are 2 sketches, and this is R75. This tool is R75. So what I've done is simply I have created the R75 radius. Okay, and to give you a idea of what will be the step over, I've just increased the diameters by 10 times. So whatever step down also you're seeing, or a step over, is going to be 10 times. So it's actually 1.5 for a 5 micron scallop. And if I go to the 16 millimeter ball nose, to get the same scallop of 5 microns, I need a step over of 0.5. Okay, so this is basically how we estimate the side step, and for this particular part based on the scallop. So you'll get this part along with the sketch, and you can see how I've created the or how I've estimated the scallop. Okay, so currently we are supporting the oval form and we are supporting the barrel form of the tool. There's another tool that's pretty, there are rather 2 more tools that are pretty much in use or are being driven a lot by the cutting tool manufacturers, and some of our competitors are already supporting it, and we'll have the support of it pretty soon. One is called taper form, which is very, very popular. If you've seen a lot of my competitors' videos, you'll see that a lot of these videos are done with the taper form tool. And then we have a tool for machining floor of the surface or floor of the part, and that is done with a tool called as a lens form tool, or a tool that has a very large radius at the bottom. Just imagine an end mill with a large radius at the bottom. That's a lens form tool. So both of these tools will now be supported by SolidCAM very soon. Right. Let's move ahead now. Okay. Let's move ahead and let's look at another improvement that we did in our version of 2018. And that's in the area of port machining. Like SWARF, we now support roughing and finishing of toolpaths in 4-axis. So if your customer has a 4-axis machine, you could actually machine a port as much as you can on a 4-axis machine without having to get into the complexities of 5-axis. So what you end up in getting is a toolpath, very nice toolpath in 4-axis. So you've got this as my roughing toolpath, and the same thing can now be done using finishing also. So you can have roughing and finishing of the toolpaths in 4-axis. Other than 5-axis, we also support now the 4-axis functionality in port machining. Okay, I'm going to show you something now that probably you'll not see it in your SP1 version, but it'll soon be into the release in the next available SP that's going to be out of SolidCAM stable for 2018. And that is a pretty interesting feature. And that's basically mirror, okay? So let's delete, I'm going to delete the toolpath. I have this part here, and I have created an HSS toolpath at this particular, using the Mac position 2. Now, what used to happen earlier is that anything you would like to mirror, you had to do it from inside. Each module of SolidCAM had its own mirroring functionality. What we have done now is we have done away with those different mirroring functionality and tried to give you a unified interface for mirroring 2.5D, for mirroring toolpaths of HSM and also HSS in one single interface. Okay, you don't have to now learn different interfaces for mirroring, different ways of mirroring. It's simple. I just right-click on my toolpath and I have the mirror function out here. Okay, and this is a unified interface for mirroring. So now you can ask where you want the transformed operations. For example, you would now like to mirror a group of operations. You can select this group of operations and simply mirror them along completely different plane, nothing related to your current coordinate system. Okay, so I could say, please mirror it not from Mac 1 position 1, but Mac 1 position 2, but Mac 1 position 1. And I would not like to use any standard planes. I want to use a plane that's there inside SolidWorks. So I would like to use a top plane here. So I'll use a selected plane, select, go here and select the top plane. Okay, select OK. Now you could say, place the coordinate system at the current coordinate system. So wherever it's going to mirror, it will create the coordinate system exactly at the same place where it was before, only in the mirrored area. So it's as simple as that. Select OK, and I have got the mirror toolpath here. Okay. Now the best part about this mirror toolpath is that, and this is going to be our unique feature. There are some, but they don't work properly. But here it's going to be a pretty unique feature. Is that I can keep the machining direction the same as my original toolpath. So if I used climb in my original operation, I can keep climb in my mirrored operation. I don't change the direction of machining. Although you can The trick is that you can actually go into the mirrored operation and you can change it, but the original mirrored operation will still have the same cutting direction as the original direction. So if it's climb on my original toolpath, I keep climb even in my mirrored toolpath. So we have now the same unified interface now for 2.5D and also for HSS, including 5-axis. What we are now working on is the same interface can now be used for mirroring HSM toolpaths, and even there we will keep the machining direction the same. We'll keep climb as climb, conventional as conventional. Okay, so this is a pretty unique thing that we introduced now in 2018. It should be on your versions pretty soon. Right. What we also did was we brought in a couple of new functionalities in 3-axis. Let's open a part. I'll open our standard part. Okay, and what I'm going to do here is I'll show you all those new functions on this particular part itself. Ever since I joined SolidCAM, I have been missing a very interesting function for stock. Whenever I used to go for demos, especially if the customers or the prospects are machining sheet metal dies, or if they're into forgings, or if they're doing castings, then they always used to ask me, can we define the stock as an offset of your current model? And my answer would be, yes, we can, but we need to do machining with a small tool and keep that offset and use that stock as our next stock. Most of the times, my demos used to end with that statement. The customer would not be very interested in going further. We've sorted this out now in 2018, and now I can define my stock not as a block or make some program and then get it, but I can just say 3D model, okay, select the part, and now I can give an offset on the part itself. So 10 millimeter offset and create the stock. So if I now say show 3D, this is how my stock looks like. So it's basically used the surface itself, and what it has done is it has done a offset of all the surfaces and created the stock for me. This is what my customer likes to see. Okay, this is his original stock. This is how the stock is going to be represented. And this stock can then be taken and carried over into my roughing operation. So if I edit the roughing operation, and if I go into the passes, I can go to the edit passes and say edit using surface. It's 0. Okay, auto updated stock, and let's save it. Let's run the calculation. Okay, it sends the stock for calculation and the part. Okay. Okay, that's done. So now if I run the simulation, go into Solid Verify, you'll see that I don't get any box or anything. I'll just directly translate the stock straight away. Okay, so this is my stock, and I can start roughing it out. No more air cuts. It'll directly cut the material wherever it finds it. It's automatically taken the high point, and it's cutting exactly from the high point. a very important and an interesting functionality that we needed, and it's now in 2018, definition of stock by offset. Okay, let's get back to our original stock. Let's say I would like to define it by a box. Okay, 0 everywhere. Okay, this is done. Now assume that instead of holding this part on a vise, this was clamped on a plate and a couple of clamps were used. So I have 2 clamps out here. Okay, a couple of clamps here. And I would now like to take these clamps into account for my machining. So I can edit this function, go into the passes, and in edit passes, we already had this gouge check by linking with clamps. But now we have an option, because I cannot be very sure where my operator is going to place. Although I'm going to give him a drawing and say, please place it here, the operator could move the clamps slightly here and there, a few millimeters here and there. So in order to take that into account, we have an option of giving an offset. And if I run that now, it'll take into account the clamps, and it will create a 3D offset of the entire clamp geometry and make sure that the tool doesn't go close to the clamps at all by that distance which we defined in the offset. Okay, that's done. So you can see that it's completely avoiding the clamps, taking into account even the offset geometry. Okay, so it's pretty neat. You can use this functionality in all of your die mold work, or even a regular part that you're using the clamps. Okay, so what we did after this was we introduced a very important feature, or very important 3-axis calculation engine called Turbo HSM. Turbo HSM is a completely new product. It's a new engine. It's based on the latest 64-bit architecture, and it has got extremely fast calculation times. Okay, it's almost like 4 or 5 times faster. That's the least. And in some cases, parts which are pretty large, it could be as fast as 50 times with our regular HSM. And if you compare it with our competition, you could take the fastest of the engines today, which many people have said, look, that particular engine is really very fast in calculation. We could be about 2 times faster than even that engine, which is considered to be the fastest engine. So what we have introduced in the Turbo HSM are few functionalities. For example, if I would like to add in the Turbo HSM constant Z, so we have got constant Z, linear, constant step over, pencil, and then we have a couple of rest machining operations using constant Z rest finish and constant step over finish. So let's address the constant Z. Let's pick a tool. Let's pick an 8-ball nose. Go to the levels. You can see that the number of parameters definition are also very, very limited. So most of the thing is being handled by the engine, the software itself. Okay, so I'll create it manually. So let's pick the boundary, and in the step down, I would say I'd like to go with 0.5 millimeter. And cutting is zigzag, machined by regions. You could also go from top to bottom or from bottom to top. I believe there were many requests, especially from the Far East side, for machining to happen from both directions, from top to bottom and from bottom to top. Currently, our HSM can do only from top to bottom. Turbo can do it either way. You can do it from bottom to top or from top to bottom. Okay, link, you can see that it's by default. There's nothing else. And most of the times, the default works very nice. Okay, so let's save this, and I'll hit the calculate button. The only calculation here is sending the geometry to the engine and receiving the result. That is the only time it takes.
Amod, we have lost your communication. We don't hear you speaking. Okay, we seem to have a little technical difficulty on Amod's side just for a moment, so please stay tuned. We'll be right back with you. You'll still be seeing the screen.
If there was some small issues in the connection, it's been restored. Sorry, I believe there was some problems in the connection. It's been restored. Right.
Yes, we hear you now well. Okay, you can go ahead.
So, like I said, if I want to make a change in my calculation, I can just go change the depth step and hit save and calculate. It's again sending the data and receiving the data. The recalculations are pretty quick. So changing the depth of cut, it did not do any serious calculation. It just did its calculation very fast and sent me the results. Okay, the same thing, if I copy it below, paste it here, if I edited this, and instead of saying constant Z, I would like to do linear, and I can go into my passes. I have got the option the same, but I've got an option to do adaptive. Okay, so when I'm using 90 degrees as my angle, there are going to be several places which are parallel to my cutting passes. And if the walls are vertical, I'll get a large step over. So let's look at how this handles it. So I'll just hit save and calculate. It's already done. The result is out. You can see that when I go parallel, that means I'm going in this way. Let me switch off the constant Z. When I'm going in this way, this wall over here will receive high side step. So in order to avoid that, oops, it's not done, it looks like. Okay, it's pretty small, so let's run. So what it will basically do is it will add extra passes to those areas. Another very interesting thing that we have is that if I decide that I would like to go between 0 and 45, okay, then I can switch on an optimum machining angle here. I don't need to define 0, 90, 45, nothing. It will figure out areas where it could machine in a different angle and some other area in a different angle, which will give it a much better appearance, a much better finish. So if I run that, okay, you can see how quickly the calculations are happening. For example, now here, you could see that the machining happened in this way. But if I go to the region here, you can see that the machining has happened parallel to one of these edges. So it is trying to keep the acceleration and decelerations pattern to minimum. It's trying to change that. And if I go to the region here, it's following this edge here. It's no longer doing this way. This would have considerably increased my cutting time. Okay, so linear machining is also very quick. Parts like these, the calculation time is, I would say, less than a second. Okay. Again, let's copy this and let's look. I'll paste this. Let me edit. So let's look at a constant rest finish that we have. So I'm going to take a tool, and let's say I'm going to use 8 corner radius 2. Let's go to the reference tool. So I can say use this reference tool. The reference tool could be a ball nose, could be a bull nose, or it could be another flattened mill also. So I can give that as my reference tool, and I can expand the rest areas by 0.5 millimeters. So it will overlap into the already machined area so that you don't get that small step-like thing that remains if you do it exactly. Okay, so let's go and say 0.3 millimeters. So my entire thing now will be machined using constant Z. Okay, as if it's doing constant Z, it will just find the areas where the material is remaining, and it will give me the result. Now, this is not going to be as fast as our constant Z, but it's still pretty quick. Oops, what happened? It did everything. I think we have a problem here, but I can show you a finished result a bit later on. But what it is actually going to do is it's actually going to run only in the corners, and that too in constant Z. Okay. Another important feature that we released in 2018 was in HSM itself, and that is 3D constant or contour rest machining. Now, contour rest machining is basically an enhanced functionality of rest machining, which basically takes into account any combination of tool. Our earlier rest machining, or the rest machining that exists in our HSM, had the limitation that it could work only with ball nose tools. With a contour rest machining, it can now take any combination of tools. You could use your previous tool as a ball nose, and the next tool could be a bull nose, or it could have a previous tool as a bull nose, and the next tool could be ball nose. So it can have any combination of tools. Right, this is another important functionality. Another nice thing that we did in 2018 was the ability to actually see only those operations that we regularly use and just switch off all those operations that we don't use to make the GUI more simplified. For example, I don't use morph machining, I don't use offset cutting, I don't use boundary machining, and I don't use, let's say, the prismatic part machining. So I don't want to see them in my list anymore. So I have an option to customize the menu, and I can switch off all those things that I don't want to see in my list. Okay, I don't want spiral, I don't want radial, I want linear, I don't want hybrid constant Z. Okay, I don't want parallel pencil milling. That's it. So now if I click out here, you can see only those operations that are visible to you, which you have selected. I don't see all those operations, and by doing this, I'm actually reducing the clutter in my GUI. Okay, now I promised you that I'll show you a part because for some reason this isn't working. So let's try and see if I can find the part. Yes, I can. Okay, so we did the constant Z rest finishing, and this is how the toolpath would look like. It will do everything in constant Z mode only, like slicing it and then generating the toolpath. Everything is handled only in constant Z, nothing else, no 3D operations in this, just pure 2.5D constant Z operations. Okay, so constant Z you could use for doing rest machining. You could also do the rest machining using constant step over, and this is how the toolpath would look like. This looks like our regular toolpath of rest machining. Only thing here is that it is using the constant step over method and not the method that we use, which generally looks like parallel pencil. But even then, we have got an option in Turbo called as pencil, and we could have, instead of a single pass, we could have multiple passes of pencil running around. Now, even this calculation, for example, is very fast. A part like this, the pencil milling could take anywhere between 3 to 4 seconds to calculate. Okay, so the turbo engine is very, very fast. what we have done further, okay, let's look at the constant Z operation. Let's edit this operation. Let's change it to 0.5. Okay, and what we introduced here is the point spacing, something again that's missing in our HSM, although we can use some trick, but we can't control the point spacing. So we have got the point spacing out here. We can now specify what is going to be the minimum and maximum distance between the 2 points and hit the calculate button. Since it's calculating a lot of points, you'll see that this was going to take a slightly longer time. Sorry. The advantage is that you could end up getting a toolpath that's very dense. Okay, so if I now run the point distribution to you, if I show you the point distribution, okay, this is how it would look like. So let's go into the backplot, run the backplot setup. This is my toolpath. And if I now show you the point distribution, you can see that it's pretty dense. Even though this area is straight, it is still putting points for you. Okay, so you can expect that the surface quality that you will get is going to be extremely of high quality because you have controlled the point spacing. Okay. We have already seen some very nice results coming from Japan for turbo. They have done a very nice comparison between HSM and turbo. They've done several cuts and the results are very encouraging. And I hope you guys also have taken out some time to test this engine, to cut some parts with it. You can actually, anyone who likes to evaluate this point distribution, please get in touch with me and I'll give you a development version for you to test it on the machine to check the surface quality coming out of this new changes that we have done with the Turbo HSM. All right, sorry for a couple of interruptions. Thank you very much for attending this webinar and I hope it was useful. If you have questions, I'm here to answer your questions. Okay, there is a question. What happens to the mirror job if the original job itself is changed? It's obviously what we are doing inside is basically a geometrical mirror. Okay, we are not doing toolpath mirror. Now that's a difference between doing a toolpath mirror and a geometrical mirror. A geometrical mirror will carry the same characteristics of your original toolpath. That's why I said we keep the cutting direction same. Okay, so if your original geometry changes, your mirror geometry also will change. Your original toolpath will change and your mirror toolpath will also change. Okay, so it is related and tightly related to the geometry. I see only one question. Okay, sorry, there is another question here. Okay, somebody asked me about how the scallop is calculated. Now, what I told you about the scallop calculation is what is called as the basic way of calculating scallop. Now, most of the softwares around today use those basic formulas to calculate scallop. because if you understand, a true scallop will never work in real world. Why? Let's come to this tool part here. Okay. Now, if I look from top, I have got a vertical wall here, and I have got a horizontal face here. If I'm machining this part, let's say along y-axis, and if the software says we can support true scallop, okay? Now, what is a true scallop? A true scallop is a scallop that will remain true irrespective of how the surface is. So basically what they will do is they will try and calculate the steepest possible surface. Let's say this surface here, and they will estimate the scallop. They will calculate for the scallop what should be the step over, or the step over in this case. So let's say I get a step over because I would like to keep a scallop of 5 microns. So for all this surface, I am going to get a step over of 0.02 millimeters. Okay, but that scallop is not applicable for this surface here, because here it's completely going to be different. So what happens in systems that say that can do true scallop is that they will apply the same 0.02 step over also onto this surface, which is sheer waste of time. You're actually rubbing the tool, not doing anything else. On this surface, on this surface, on this surface, and on this surface, it's sheer waste of time. Actually, 90% of that area is sheer waste of time. Just for the 10%, you are wasting cutting time on the other 90% area. Better would be to just ignore this area and machine this in a different way. That's why most of the softwares that are available today use the basic formula of calculating. They assume it's a flat surface, and on the flat surface, they'll calculate the step over based on the scallop that you have defined. There are formulas. Now, what I showed you was the most basic way of calculating a step over based on your scallop. There was another question here. Yeah, that's it. I think this is all. If you have any more questions, please let me know either now, or you could email me your questions or Skype me your questions, and I'll be more than glad to answer your questions. If there are no more questions, I would like to end this webinar here, and thank you very much for attending the same, and have a nice weekend.
And thank you very much, Amod. And I repeat again, this webinar was recorded. It will be available in the reseller area. Everyone have a nice weekend. Bye-bye.